You ever stop and wonder what's actually going on when you cook an egg, or why an apple slice turns brown after a few minutes? Well, I'm here to tell you it's not magic, it's chemistry. And today we're going to pull back the curtain on this incredible, invisible world of chemical reactions that's happening all around us all the time. So here's our game plan. First, we'll start spotting chemistry in just everyday life. Then, we'll learn the telltale signs that a reaction is happening. After that, we're going to learn to speak the language of chemistry and then tackle the super important skill of balancing equations. And finally, we'll uncover the universal law that holds this whole thing together. You ready? Let's dive in. All right, first stop, let's just look at some things you've probably seen a million times. As I go through these, I want you to ask yourself one question. What's the one thing that all of these have in common? I mean, really think about what's happening to the stuff involved. Think about it. Milk going sour, an iron pan getting all rusty, cooking food, or even just digesting it. In every single one of these examples, the stuff you started with is transformed into something totally new. The milk isn't just warm milk anymore, it's sour. The shiny iron becomes this flaky, reddish rust. The very identity and nature of the material changes. And that is the heart of a chemical reaction. Okay, so if we can't always taste our science experiments, and seriously, please don't do that, how do we actually know a chemical reaction is underway? Well, thankfully, there are clues. There are signs we can look for to spot the evidence. Now, this is a classic. You start with a simple strip of magnesium ribbon. It's just a kind of dull, silvery metal. But when you burn it, whoa, it just erupts in this dazzling, super bright white flame. And what you're left with is this crumbly white powder. The magnesium has literally grabbed oxygen from the air and become something brand new, magnesium oxide. It's a perfect and really cool example of a chemical change. That magnesium reaction actually showed us a couple of key things. We definitely saw a change in color, right? It went from silver to white. And we for sure had a change in temperature. That flame was incredibly hot. Well, those are two of the four big signs of a reaction. The other two are a change in state, like a liquid turning into a solid, and the evolution of a gas, which you'd see as fizzing or bubbling. If you spot any of these four things, chances are you're watching chemistry in action. Okay, so you're basically expert reaction spotters now. But how do we write down what we saw? Scientists need a really clear, simple way to describe these reactions so that anyone, anywhere can understand them. It's time to learn the language of chemistry. We could just start with a sentence. I mean, it's accurate, but it is so long and kind of clunky, isn't it? Can you imagine writing that out for every single reaction you study? No way! There's got to be a better way. And there is. This is a word equation. It's much shorter and gets straight to the point. On the left side of the arrow, you have your starting ingredients, magnesium and oxygen. We call those the reactants. And on the right side, you have what you end up with, magnesium oxide. That's called the product. That arrow just means turns into or yields. Simple, right? But to be as efficient as possible, chemists use symbols in a chemical equation. Mg plus O2 yields MgO. This is the universal shorthand. It's clean, it's fast, and it's packed with information. But take a closer look at it. Is it completely correct? Is there something a little off here? And that question brings us to our next crucial topic. See, just writing down the symbols isn't the whole story. A proper official chemical equation has to follow one of the most basic fundamental laws of the entire universe. It has to be balanced. So let's go back to our equation. And I have a question for you all. Take a good look. Is this equation balanced? Meaning, is the number of atoms for each element the same on both sides of the arrow? Or is it what we call a skeletal equation? Go ahead, pause and count them if you need to. All right, let's tally it up together. On the left-hand side, the reactants, we've got one magnesium atom. And on the right, the products, we've also got one magnesium. So far, so good. But now look at the oxygen. We start with two oxygen atoms on the left, but we only have one on the right. Uh-oh, they're not equal. That means this equation is unbalanced. We call this a skeletal chemical equation. It's just the bare bones of the reaction. So the big question is, how do we fix it? How do we get it to balance? Don't worry, it's not as intimidating as it looks. In fact, it's kind of like solving a little puzzle. Let's walk through the steps with a new example. Okay, here's our new challenge. Iron reacting with water to make iron oxide and hydrogen gas. You can probably see right away that this one's all out of whack too. I mean, we've got one iron on the left and three on the right. Let's get this thing balanced. The way we do this is with a bit of trial and error. First, imagine there are boxes drawn around each chemical formula. The most important rule is you can never change what's inside the box. So H2O will always be H2O. All we can do is change the number of boxes by putting a number, a coefficient, out in front. So we'll start with the most complicated thing, which looks like that Fe3O4. We see 4 oxygens on the right, so we need 4 on the left. Let's put a big 4 in front of the H2O. Great, oxygen is balanced. But now that gives us 4 times 2, or 8 hydrogens on the left. No problem, we'll just put a 4 in front of the H2 on the right to make 8 hydrogens there. And last, we have 3 irons on the right, so we just need to put a 3 in front of the Fe on the left. And there it is, our final, beautiful, perfectly balanced equation. Let's do a quick final check, like all good scientists should. Left side, 3 irons, 8 hydrogens, 4 oxygens. Right side, 3 irons, 8 hydrogens, 4 oxygens. Perfect match. It is balanced. So you might be wondering, why do we go through all this trouble? Why is balancing so incredibly important? Well, it's not just some random rule for a science class. It's about respecting a law that governs everything in the entire universe. And it all comes down to this fundamental principle, the law of conservation of mass. Basically, it says that matter can't be created or destroyed during a chemical reaction. The total mass of all your reactants on the left has to equal the total mass of all your products on the right. You have to end up with the same number and type of atoms you started with. They just get rearranged. This is the key. Write this down. Mass can neither be created nor destroyed in a chemical reaction. The atoms are just shuffling around, breaking old bonds and forming new ones to create new things. But the atoms themselves don't just pop into existence or vanish into thin air. So when we balance an equation, we're really just doing the bookkeeping to prove we followed this fundamental law. So there you have it. From spotting the signs of a reaction to balancing the equations that describe them, you now have the basic tools to understand the chemistry that's constantly happening all around you. So my final question for you is this. As you go about the rest of your day, where else are you going to see chemistry in action? Thanks for joining me in the lab today. You ever stop and watch